In 2016, Maverick Applied Science developed the Plant Engineers FRP Forum to create a platform where plant engineers could come together for in-depth discussions and to improve their work and knowledge of non-metallic piping and equipment. After the success of the initial Plant Engineers Forum, Maverick decided to offer this training yearly. The third annual Maverick Applied Science FRP Plant Engineers Forum was held on May 9th and 10th, 2018. This year's forum included presentations by key Maverick employees, along with a broad group of industry leaders. This year's topics included what proper non-metallic equipment purchasing specifications should include, how to choose the proper materials and manufacturing methods, how to design internal structures, and how to choose the correct codes and standards for fabrication of your non-metallic equipment. Finally, we also included some inspections of non-metallic equipment. Since everyone was not able to attend this forum, Maverick would like to share some of the offered presentations to the public. Thank you for your interest in Maverick Applied Science.
Okay, as mentioned, Tom Haber with Maverick, and I kind of lead the inspection group. That's my basic goal in life. I also do a few inspections here and there. But typically we have a group of inspectors that travel around the plants in different places. So, and my primary focus is leading that group. The first talk today is about glass reinforcement. This is kind of a basic, good morning, how are you? Could be your first cup of coffee. There's nothing too technical about this one. So this one's going to be a fairly easy and a fairly quick one. The goals of the presentation are to explain the basic reinforcement types that you'll see in a fiberglass fabrication of a tank or piping. So we're going to go into the single end roving, the chopper gun roving, the way woven is made, and then we're going to talk about how the different parts of a fiberglass tank or pipe are made, the corrosion barrier and the structural wall, and how the different reinforcements apply in that. The starting point of most reinforcements for fiberglass is a single end roving. The single end roving is basically glass strands that are pulled and then bundled together into a strand. The strands, individual strands, are measured in microns, so they're very small. And there's hundreds of them packaged into a string, basically, into a packaged piece of string. And then those pieces of string are used to reinforce fiberglass. Similar to single end roving is chopper gun roving. And chopper gun roving is the same basic thing, it just doesn't have a lot of binder to hold the glass together. So when the pieces of chop are run through a gun and it's cut into the 1.5 inch, give or take, long pieces, those pieces are sprayed in random pattern. And so because there's not much binder holding that string together, you get better coverage. So that's chopper gun roving. Woven roving is basically the single end bundle roving woven into a fabric. And that fabric gives you strength in different directions. Typical woven roving gives you primary strength in 2 directions. But there are also other fabrics like unidirectional and some fab mats and things like that that will give you strength in different directions if you need. Beyond that, chop strand mat is one of the basic building blocks of fiberglass parts. It's used in corrosion barriers and structural laminates. There are parts built strictly from chop strand mat, and that's all you would need. Chop strand mat is basically these single end rovings chopped into a random pattern and sprayed onto a flat area. And that rolled good is then applied as a structural reinforcement when it's saturated with resin. Finally is veils. I won't go as deep into veils as you might expect because Daryl's doing another presentation later strictly on veils that will tell you what's the best practice that we've found and some of the confusing things we've found about different veil applications. So, single end rovings. Single end rovings are basically glass melted, and then as the glass comes down, it's pulled into a filament, cooled, and then they're bound together. The size applicator, size is an odd name for me, I've never understood that. But they call the sizing part of what holds the glass together. So then once it comes out from the bottom of this strand here, it's wound around a krill, and it's made into what they call balls, or there's a lot of different names for them, but yeah. But this is then taken and wound, so you would have a package of 50 to 100 of those set aside, and each end would be pulled through resin and then used for filament winding. So that's kind of how glass is made. One of the important things I've seen in specs that would be good for you all to know is sizing. So the single end rovings come in different sizes you can buy. For instance, 113, that's 113 yards of that fabric is taken to make a pound. That's how they set the sizing. So the smaller the number, actually the bigger diameter the glass strand is. 113 yield will give you a very ropey pipe. It's such a thick glass that when you stack it all together and make a winding band out of it, a lot of times you'll see bridging because the pattern will be so thick. So a lot of times, unless it's big diameter pipe or big diameter tanks, 113 yield isn't very common. 250 yield is probably the most common that's used out there. And as you get smaller and smaller, if you make 1-inch pipe, you'll use other different end rovings. Chopper gun. There's a lot of different ways to apply chop. This is a basic ball of chop that you see here sitting on the carriage, and the spray is coming out right here. So there's one strand run through a gun. It's easier to see here, I guess. The strand runs through the gun, is chopped into random length pattern, and then resin is sprayed along with it to basically make chop strand mat, wet chop strand mat as it goes along. Some of the difficulties with this is if you do it by hand, it's very difficult to coordinate how much you're getting on in place. If you use roll goods, you know you're getting 1.5 ounces of chop strand mat in that location. Depending on how well calibrated that guy's hand is whether or not you'll get 1.5 ounces per layer if he's doing it by hand. Woven roving. Woven roving is a primary structural reinforcement for fiberglass. It's applied in a lot of different ways. It's going to be rolled goods. Rolled goods need to be stored dry. And then typically a long roll, 50-inch roll, is cut down into varying widths to make welds or to apply to a mantle. You'll see big woven roving used for dome fabrication or something like that, or a bottom, and then spiral wrap woven to create a pipe or a tank, create a structural wall for that. The most common sizes of woven roving are 18 ounce per square yard and 24 ounce per square yard. Same basic theory as the winding glass. The bigger is thicker glass, heavier reinforcement. The other wovens, the other structural reinforcements you'll see, such as woven, like unidirectional, it's always hard to see in a picture, but basically all the strands in this glass are vertical, and they're being wound in, but this gives you only strength in the vertical direction of this vessel, so in the axial direction of the vessel. Fab mats and stitch mats, we don't typically recommend because they can become very difficult to wet out. As you see with this, you basically have a chop strand mat and a woven roving attached to each other, stitched together. The amount of resin it takes to wet that out, both sides, is not common. So a lot of fabricators end up putting some of that on dry. Dry will leave you voids. Voids are bad in fiberglass. So we're not big fans of fab mats or stitch mats unless they're used in the right, there's a very few locations, maybe for the flanges, for the back of a flange when you're just trying to build thickness. There's always a lot of resin in a flange that ends up saturating down, so typically saturation is not a problem for fab mat and stitch mat, but it's not an easy fabric to work with. Chop strand mat is probably one of the most basic building blocks of fiberglass parts. Chop strand mat used for virtually everything. It can be the only structural reinforcement at times, or it's used as a bedding layer in between wovens. Woven roving layers typically do not do well back to back with each other. You need some kind of a bedding layer in between them to separate them a little bit. So what you'll see is chop strand mat used for that, in addition to just being, again, the primary structural reinforcement for a vessel or a flange. You'll hear that called type 1 when it's only chop strand mat. But there's a lot of standard developed procedures out there for type 1 mat. Thicknesses are known. It's a very well-known commodity. Surfacing veils, just a little bit on surfacing veils because again, Daryl's going to go much deeper into them. Surfacing veils are what holds the resin against the corrosion, against the primary fluid. So a surfacing veil is going to hold 90+% of its weight in resin. Resin is what's corrosion resistant, not glass. Glass can carry some corrosion resistance, but the primary function of the glass is to hold the resin together. Resin being primarily the corrosion resistant part of this. You want as much resin as you can get against the sealing surface to stop corrosion. So the fact that these bales hold 90+% of their weight in resin gives you a very resin-rich surface where the corrosion is primarily going to take place. There's a few common types of surfacing bales you'll see. C-bale is probably the most common. C-bale is used almost everywhere. Everyone will know C-bale. It's a corrosion-resistant surfacing bale. It looks bigger in aperture here than it really is. It's like tissue paper. It's very fine, so it tears easy. ECR bale is another blend of C-bale using different glass inputs that has enhanced corrosion resistance and is becoming much more popular in some applications for different chemicals. Nexus also has its own place in different chemicals. Daryl, again, will go deeper into that. And then carbon bale. Carbon bale is used a lot of times for either conductivity or high heat resistance in a corrosion barrier. There are other bales such as Halar, Kynar, and specialty bales, especially carbon bales, but those are not very cost effective yet, and they're not widely used in the industry. I dare say you probably won't see them unless you have a very specialized vessel. So a little bit about how stuff is made. Typical fiberglass laminate. If you assume this block here is basically this. So the first yellow layer is the veil layer. And that surfacing veil, again, is holding so much resin up against the process fluid that that's what provides your primary containment of the fluids. This is going to have 90% plus resin. The following layers, which are typically chop strand mat layers, either sprayed or rolled goods, they're going to have 65 to 70% of their weight in resin, depending on how well it's wet out. So you can see as you go through the structural wall, the amount of resin in the laminate gets lower. And as you go back through the secondary structural layers, those layers can have only 35 or 40% of their weight in resin. So one thing to keep in mind with this too is once you see corrosion has gone through your primary corrosion barrier and is into your structural laminate, because the percentage of resin is much lower in the structural laminates, it will typically accelerate the corrosion through the structural wall much faster than it went through the corrosion barrier. Because the corrosion barrier is built to stop corrosion. Structural wall is built to help hold the corrosion barrier together. When you first start putting down a corrosion barrier, again, because this is the most critical part of your vessel, this is where your vessel is going to stop leakage, is the corrosion barrier. You want to make sure everything is sealed tight and well built in the corrosion barrier. A vessel that has some air and some issues with the structural wall, there's enough structural wall typically and enough safety factor that you won't have a major issue. But if you have a small issue in your corrosion barrier, your vessel will leak eventually. So if you're doing inspections and stuff like that, you want to make sure your corrosion barriers are very tight. Different bales and different fabrics don't work well with corners and edges if you're making a flange or if you're trying to make a dome like this. With carbon bale doesn't like to bend. It's stiffer. It doesn't like to bend until it's saturated. And once it's saturated, it likes to lay over on itself. So again, it's difficult to see, but you can see wrinkles in there where the carbon bale is trying to form around that knuckle. If you're putting it on a mandrel, typically it's not hard. You have to make sure your overlaps are right. Overlaps are critical, especially with veils. But on mandrels and flat surfaces, all these veils are fairly easy to apply. But as you build a flange, or you weld the neck of a dip tube or something in, some of these veils are much more difficult to work with as a fabricator. So even though you think you're doing a good thing by using carbon veil, if your fabricator is not well versed in carbon veil, you may not get a good part anyway. You may end up shooting yourself in the foot a little bit. As discussed before, one way to put on gun roving or chopper gun roving is with a hand applied chopper gun. There are places where it's effective on a dome or a unique part, something like that. It's not as easy to take chop strand mat in a roll good and lay it across that, much like you saw with the carbon veil. Things don't like to fold, they don't like to roll over. So if you use the hand chopper gun on this part here, you would probably get good effective coverage and you wouldn't have a lot of extra double overlaps like in the center. Typically though, if you want to make sure that your corrosion barrier has the right thickness, has everything you ask for, if you use rolled goods with a proper overlap, 1.5 to 2 inches of overlap on your edges, you'll get the thickness that you're expecting. So that's an easy way to verify that you are getting what you want. If you decide to allow mechanical applied chop or even hand applied chop, it's not uncommon to require your vendor to add on a percentage, say 25%, to that corrosion barrier to ensure that you're getting the thickness of the corrosion barrier you want. So if they want a hand chop or mechanized chop, it's common to increase the thickness of the corrosion barrier a little bit to ensure you get the full coverage you want. We're not going to talk a lot about dual laminate vessels today. We will have some other thermoplastic talks coming, but if you have to buy a dual laminate vessel, you're in a very specialized area. There are unique things that go with dual laminate vessels. Basically, the corrosion barrier is the thermoplastic, and then the fiberglass is used as a structural cage for that. So these are a little bit unique. If you have a need for a dual laminate vessel and you don't have a lot of experience in that, I would suggest you find the experience to help you with that. Okay. So, different ways you can build things now. Contact molded or filament winding. Both have their strengths, both have their weaknesses. Contact molding of a laminate is either going to be what we'll call typically a type 1 or a type 2. Type 1 is only going to have chop strand mat. Type 2 will have some kind of a directional reinforcement. Woven roving, unidirectional. I think officially if you use type 2 it has to be woven roving per RTP1. So, but a type 2 structure has a different makeup of the laminate package. And then type X or filament wound structures, you see down here. So contact molded structures have a much higher content of resin in them. So for instance, paper mills recommended using contact molded piping for years and years and years because the corrosion resistance of that piping was thought to be higher because there's a higher resin content in that pipe. Filament winding is stronger and typically will be thinner because of that strength, but the corrosion resistance of that structural layer isn't nearly as much because there's, again, 80% of the structural package in the winding band is glass. So there's only 20% resin in that package. So it's not nearly as structural resistant, it's chemically resistant as a structure built contact molded. One other point I had and I forgot to mention there, also depending on the size and the shape of the vessel will depend on whether it's going to be filament wound or not. If you have a rectangular vessel, it's not going to be filament wound. If you have a small 6-inch diameter scrubber vessel, Venturi, it's probably not going to be filament wound because something that small is typically always going to be made by hand. Okay, so structural walls on a contact molded side. So again, type 1 would be just chop strand mat layers. That's all that would be in that wall other than a veil. There's a lot of data out there for engineering and design, how to design a tank or a piece of pipe using type 1 laminates and type 2 laminates. It's probably the most common way to make fiberglass out there. If you have a mold and resin and catalyst, you can make type 1 laminates. That's part of the problem with the industry is that there's a lot of me toos out there because it's a fairly simple way to do stuff. Filament winding. Filament winding is a band of those single end rovings packaged together, run through a resin bath over here, and comes off wet. And as that wet band is wrapped around, you get strength in different directions. You see this has angle to it, so maybe a 70-degree wind angle, so that gives you some axial strength, primarily circumferential strength. On a hoop wound vessel, you're getting primarily circumferential strength, and they'll put in unidirectional glass typically to give any axial strength they need. You can set the strength of a pipe or a tank based on the wind angle. So on a pipe, we were always taught a typical perfect wind angle for pipe is 57 degrees? 54.7 degrees. So And that optimizes the strength in the circumferential direction and the axial direction. So for a piece of pipe, you want burst and you want axial strength. On a storage tank that's atmospheric, you don't need as much axial strength. So you'll typically see more winding in the steeper winding, say 70 degrees or something like that, to give you a better wind angle to match the circumferential strength you need. And as I showed in the previous slide, there's a couple different ways to wind. You can either wind horizontally, where the mandible is pinned and spins horizontally, or vertically, where the mandible sits flat and spins vertically. Pros and cons to both. Horizontal winding is probably easier because the resin stays in situ a little bit better. When you go to vertical winding, the resin you spray on top wants to come down. Newton was right, there is gravity. So with vertical winding, you have to have resin technology very well dialed in, or else all the resin drains to the bottom before it can start to cure. Vacuum infusion is still fairly rare. There's some companies that do very well with vacuum infusion, but they are far and few between. Vacuum infusion provides a really high strength part. It is much higher in resin content, in glass content typically. So these parts can be less corrosion resistant. If you need a corrosion resistant part that's vacuum infused, typically there will be a secondary corrosion barrier added, or the corrosion barrier will be put down first and act as the initial boundary for all the other glass fabric to be vacuumed to. Still not very common. You will only see it in your highest end manufacturers. And the end of my statement is resin is the corrosion resistant part. So depending on what you're doing, if you need high corrosion resistance, make sure it's got a lot of resin and the right resin in it. If you need high strength, all the glass you can get in is better for you. So that's kind of how they're separated. Any questions?